microwave antenna people have so much of well-known solutions for this, and those solutions actually makes this millimeter waves propagation possible for longer ranges. And as far as the current 5G is concerned, 5G have basically two, or particularly two operational bands. One is a legacy band, which we also call it at sub-6 gigahertz bands, and the second one is the millimeter wave band, which we call it as new band, where the peak data rate uh, expected was around 50 Gbps or so, and so forth. The current data rate for sub 6 is this around expectancy is 1 Gbps. However, at laboratory level, even we have also achieved around 600, 700 Mbps kind of speeds at sub 6 gigahertz. So these are some of the requirements, and these are some of the frequency bands as far as the use cases are concerned. So here on the chart, you can see like what frequencies are being used for what technologies in terms of 5G and 6G in particular. So for 6G, the futuristic discussions as far as the worldwide technologists are concerned in ITU meetings and IMT 2030, those kind of considerations. So there are several frequency bands which is promising. One of that is this W band and the G band, where in W and G band uh, on-demand data requirements, although the coverage is a limitation, but in those cases, these two are again one of the most promising one. However, for coverage kind of stuffs, FR3 band of 6G can be near around 7.1 to 5 gigahertz or something. But as far as Indian aspects are concerned, this frequency band is one of the major interests. So this is one of the white paper, particularly as a list of probable 6G technologies. So as far as we antenna technologies are concerned, for we, three particular technologies like OAM, which is basically orbital angular momentum multiplexing. Multiplexing is a technique. However, this OAM stubs we also design for antennas. So we call it as OM antennas. So the second one is the RIS, reconfigurable intelligent spaces. These are the kind of surfaces which have partial intelligence, uh, which is developed artificially by designing proper surface. And when we make it reconfigurable, then it becomes simply the reconfigurable intelligent surfaces. And the base of these two technologies are none other than the metamaterials. So the metamaterials are the main fundamentals which is going to be in the base of these two major technologies. So just having a look on the Bharat 6G vision, where the complete designing and development of 6G network technologies that provides ubiquitous, intelligent, and secure connectivity for high quality living experience for the world. So basically, this is the tagline for Bharat 6G vision statement by Government of India, Ministry of Communication particularly. So the idea is to design, develop, and deploy a complete 6G technology indigenous. So out of this Bharat 6G vision, uh, we are proud a member as part of Bharat 6G terahertz testbed team, where we are developing one of the testbed where sub-terahertz band of the 6G proposed band. It's not the exact and final band, which can be tested. So a consortium was made by Ministry of Communication, where Samir, IIT Madras, IIT Patna, IIT Guwahati. So all we four are one of the biggest consortium which is working on this Bharat 6G terahertz test bed, and we have different steps to design and develop. So on this current screen, I have presented the possible use cases while integrating intelligent reflecting surfaces and antennas in both of the environments, like indoor environment as well as outdoor environment. Out of these diagrams, there may be several different use cases. also maybe particularly identified for defense, maybe particularly identified for some disaster use cases, and so on and so forth. So these techniques have uses in both indoor and outdoor environment, and these surfaces have specially designed quality in itself through which the direction of beams can get manipulated. Manipulated the way it needs to be, the same needs to be designed by the designer. The way it is intelligently designed, optimized, again, exactly in the same way, the beams can have maximum efficiency in that way. So the beams can have the scanning quality as compared to uh, the normal phase shifted antennas like array and phase shifters like active antennas kind of stuffs, phased array kind of antennas. So in those kind of use cases, if you see, there are so many active elements in the backend who are power hungry, and as far as the circuitries are concerned, that is also one of the complex, the challenging one. And exactly to make these surfaces reconfigurable, we also need some switching elements. So depending on the frequencies, those switching elements can be selected in that appropriate way, and accordingly these unit cells, these reconfigurable intelligent surfaces can be designed, and the beams can have the steering capability. As far as our lab is concerned, we have achieved up to plus minus 75 degree with scan loss of maximum 2 dB, so and so forth. Now I will be just presenting some of the works which is already well published from our group, and we have full facility related to the designing, analytics, fabrication, testing. So we go for the product level development. So as of now, the first work is like active beam steerable digital metasurface lens antenna for millimeter wave application. So this particular small block which you are seeing is a kind of small bit which we call it as unit cell. As far as our surfaces are concerned, this unit cells plays very active and important role. So the way unit cells are designed, the way unit cells have the kind of characteristics, in that form itself, the surfaces will have the qualities, the properties. So the major concern for a designer always lies how well optimized unit cell can be designed. And that's why the unit cell design needs a bit of engineering in itself. And again, it's not like any inherent kind of shape, sizes, which just came in your mind and just have a patterning on the surface. It's not like that. So it originates from circuit, and then circuit gets transformed into strip line structures, and then after the kind of complete shape of unit cell comes. So these are different ways how we design our unit cells, and then we go for the optimized surface level design, where if you can see on the current screen, there are several rectangles with different color codings. So that simply represents four different types of unit cells and its placement over the surface. These four different types of unit cells are basically modified version of the same fundamental unit cell. Means four different unit cells are created from this diagram, this unit cell itself, by changing some of its geometrical parameters. By changing some of its geometrical parameters, the kind of characteristics like the transmission or reflection magnitudes and phase of these unit cells can be optimized, and those phases which needs to be on the surface at a particular coordinate, the similar unit cell placements should be done. So this is something which we call it as the discretization of complete continuous phase surface on the reflector panel surface. So this is a discretized version of the same surface. And here we have the four different variants of the unit cell. Hence we call it as 2-bit 2-bit quantized phase distribution surface or 2-bit quantized transmission surface. So depending on the quality of unit cells, this can further get extended to multiple bits also. So and every unit cell have its own limitations. It cannot be of n bit uh, quantized phase distributions because the unit cells and its variants should follow some straightforward guidelines. And then after the kind of feeds which you design, depending on that, the integration of these kind of surfaces with the antennas needs to be done. So on the current screen, we have the primary feed as of now. Here I have the three elements, and the three elements, all these three elements are switchable actually. So on the surface, you can see the pin diode switches and the respective bias lines. So depending on the supply, depending on the requirements, we can generate one bin at a time or three beams all together at a time, two beam at a time. So depending on the possible switching configurations, the respective antenna elements can get excited and the respective beams can get generated. That means when the surfaces and antennas will be integrated, the integrated version will have very excellent quality of multiple switchable beam formation, which will be having a quality to steer also. So this particular work, when we fabricated completely in-house, and then we measured the same, and this particular one gives very nice performance. As of now, just I have shown the three beams respective gains along plus minus 30-degree direction and broadside direction. So the overall, if you see, very nice gain pattern also, and as compared to the primary feed, uh, gain enhancement for the complete operating band of the antenna around 12 dB, which can get achieved by this kind of designs. And one of the major beauty of this kind of designs were its aperture efficiency. So if you may have seen, these are highly aperture efficient surfaces, and hence their aperture efficiencies are approximately 71% and even more than that in some cases. Now, the major limitation of the previous work was slightly narrowband, not of much narrowband. However, this is slightly wider version of the same antenna or the same technology. So this particular antenna is going to act for wide bands. Now, for wideband, the idea to have wideband operation is these antennas can be wideband if the first can be like the feed antenna itself is wideband. The second, the surface if itself is wideband. When both can get integrated, then overall wide performance can be achieved. So this is overall scenario like how the wideband performance can be achieved. That's why the concentration lies on wideband design of the unit cell, first step, and then after wideband design of the surface, second step. And since the operation needs a wideband operation, wideband feed also. So the third step goes on wideband feed. So one of the well-known wideband feeds, simple antipodal Vivaldi antenna for the required band, and its designing technique is very well defined. And depending on that, this antipodal Vivaldi antenna can get integrated with the wideband surface. And while integrating these two surfaces, this is the fabricated hardware. And this complete surface, if you see, they are designed by using this as unit cell. And again, as I am showing you different shape sizes of the unit cell, that doesn't mean any kind of shape, any kind of shape will give you the performance. The unit cell design always should start from the circuit level, which we follow at our labs. So here the wideband performance analysis. So the wideband reflection, which you can see by using this red curve. So very nice, slightly wideband performance, which we have achieved for this unit cell, like from around 25.75 gigs to around 32 gigahertz. So very nice reflection in this particular band, and hence the effect of that, which you will see, wideband gain enhancement as particular to this particular graph. So antipodal Vivaldi antenna is quite operational from 24 gigahertz to 32 gigahertz. That means approximately 8 gigahertz of the band. And for this complete band, if you see the very nice gain enhancement of this complete band, which you can see, and the maximum gain enhancement at the design center frequency around 15.6 dB and so on and so forth. Even further more gains can be achieved. Again, for that purposes, redesigning of the surfaces, reappropriation of the surfaces, and all. These surfaces also have the quality of steering the beams. So very nice beam steering performance, which you can see over here, and very minor scan loss. So here we say the scan loss of around 1.6 dB for this complete plus minus 60 degree scan. And it's for complete plus minus 60 degree scan loss of 1.6 dB, very marginal, very less. Normally, by using active phased arrays and those kind of active antennas, this kind of losses for plus minus 60 degree goes beyond 5 dB or even 6 dB also, or even more. So these are some of the major results. And then after this is third work in the same sequence, which we call it as Huygens metasurface. So Huygens metasurface is different variety of metasurface in itself, which have Huygens resonance quality. And Huygens resonance is a particular type of resonance which is defined where both resonances, electric and magnetic kind of resonances, can be achieved from the same surface, from the same unit cell kind of approaches. So the idea is achieving electrical resonance on the surface and achieving magnetic resonances along the surface. So depending on that, the kind of designs are being done. Like if you see, this is the fundamental unit cell, and this is one of the top layer, bottom layer kind of structures. And there are very symmetrical kind of analogy which you see on the top and bottom surface. There is a kind of common region in between, like this particular common region, if you see, this particular common region, if you see. So on the top and on the bottom, in between top and bottom, the dielectric. And because of having this dielectric top and bottom structures, the kind of common interference, and hence the electric and magnetic resonances. So electric resonance on and magnetic resonances along. And depending on that, this reflection kind of characteristics. So after that, we have designed some variants of the unit cell and again distributed over the surface. This distribution on the surface is also proper optimization technique. As I said, the way these phases, these surfaces will get quantized, the same way the performance of this kind of surfaces will be. As of now, until now, probably we have demonstrated one transmission kind of surface and one reflection type of surface. This is also another reflection type of surface. And all these surfaces have its own inherent qualities. So, for example, like if you see this one, so this is the Huygens uh, beta surface, like this one. And when excited by this feed, and here the reference horn antenna, and the full measurement setup. And here, if you see one of the nobility, like this particular surface is very wide band, and that's why the feed also which we have used is K-band horn, and this horn is also not the simple one, additively manufactured horn, and the inner one we have metallized, and we have excited this by using standard K-band waveguide feed, and we have tested it in a quick chamber further on. And again, uh, the kind of expected performance like uh, wideband gain enhancement performance, multiple beams, and uh, the enhanced radiation characteristic. So in this case also we have the kind of aperture efficiency of around 70% or so. Now in the same sequence, there are some technologies which we have tried and we demonstrated using additive manufacturing techniques. Like one of the simplest example of additive manufacturing technique is 3D printing. So we have utilized 3D printing techniques for designing wideband, high gain, transmission and reflection type of antennas. So one of that is presented over here, and this is the unit cell design. And again, the unit cell design here also followed some standard design rules, and then after the respective reflection magnitude and phases of this particular unit cell. So if you see the reflection magnitude itself, it is covering 16 gigahertz to 40 gigahertz, and even it's better, it's more than these frequencies. However, in this graph we have shown from 16 to 40 because the measurement lies in these frequencies. So these particular unit cells have one of the advantage of achieving very wide and nice performance. So that's why this unit cell we have selected by using this additive manufacturing technique. And then after we have also performed the polarization checks with different angle of incidences, and then after change in the characteristics, the reflection magnitude and phases, so the respective amount. Now, by using those unit cells and the distribution over the surface, here we have 8 variant unit cells. So 8 variant means we have 3-bit composition and hence the respective distribution on the surface. And the feed horn is also K-band additively manufactured, and the feed is in offset, and hence the complete surface design is also offset. And this is the complete design in for analysis. It's a radiation pattern and all. And this is the final fabricated hardware prototype. So the complete 3-bit distribution over here, 8 different states, and this hard, as I said, additively manufactured and feed by this standard K-band waveguide. And here the complete setup is in test with standard horn antenna in chamber, and see the nice performances from 28 gigahertz to the complete 40 gigahertz. Here we have presented 3 sample points like 28 gigahertz, 32 gigahertz, 36 gigahertz, and so on and so forth in different E and H planes. Uh, so the on for the earlier work, which we can see is wherever ultra high widebands are needed, additive manufacturing is one approach to which these things can be achieved. In the same sequence, now we have tried several techniques on the surface, planar surfaces, using lithography kind of approach for getting highly directed reflected beams digitized, and multi-beam kind of quality. Like the major intention is how we can achieve more than one beams from the same primary radiator without using any splitter, any extra active network for the same. So for that purposes, the first is we have designed very wide and high gain reflector reflectory kind of antenna for this 25 to 35 gigahertz band, and this very nice performance. And again, by using fundamental unit cells, the distributions, the excitation, the respective radiated beams, and these are the different surfaces, fabricated one, and different surfaces like from first, second, third, these surfaces will give different responses, different beams. Different beams means beams in different directions. So this is the surface who will give beam along broadside. This will give along plus minus 15. This will give along plus minus 30. And these are the kind of surfaces are static. In the next, I will show you like how we have made the surfaces how we have made the surfaces active. As of now, these surfaces are passive. So for a given design, for example, this one, the broadside, for this one plus minus 15, for this one plus minus 30, and the same respective beams and the respective gains after doing the measurement, simulation, and analysis. Furthermore, we have extended the similar analysis for 38 gigahertz band requirements, and we have done and we have followed exactly the similar procedure. Have two variants of the same unit cell. Just you can see on the current diagram, two different shapes and sizes of the same structure. So here we have the two variants, and hence we call it as one bit configuration. And this surface, again, designing procedure of the surface remains same. So the surface and the feet, again antipodal Vivaldi. While having this Vivaldi exposing the surface, this Vivaldi normally it will have the wide radiation pattern. So this is the radiation pattern of the antipodal Vivaldi. When you integrate this antipodal Vivaldi with the surface at optimized integration, it's not like at any point, any place, you simply put this antipodal Vivaldi and you will get very narrow beam. It's not like that. So this antipodal Vivaldi having wide band radiation, when you expose this, then the kind of narrowed, highly directed reflected beams you can have. So this is the final fabricated one, top and bottom layer. And then after this is the antipodal Vivaldi in fire direction, the beams exposing the surface and getting very narrow beam. And because of this very narrow beam kind of capacity, significant gain enhancement. Very narrow means as of now its beam width is around 3.5 degree. Even if you want to achieve more narrow downing, that is also possible. Again, for more narrow downing, the surface needs to be again further larger size, and by more narrow downing, the gain in aperture efficiency that can also get enhanced. Then after we have integrated the similar approach for getting multiple beams. Multiple beams means we tried the same antipodal Vivaldi, which I have shown on the previous screen, like this antipodal Vivaldi, where this antipodal Vivaldi have this white radiation pattern. We tried engineering with this surface so that we can split this beam of antipodal Vivaldi into more than one. So initially we tried for getting two beam formation. Later on we also tried four beams. So here on this current screen, if you see, this is the same radiation by this antipodal Vivaldi, and this is different engineered surface from the same unit cell, engineered over the surface in terms of their distribution. And this particular wide radiation of antipodal Vivaldi now split it into four different beams in four different directions. So this is something like both of these are the simulated one over CHT microwave studio, and hence these are the kind of respective beams uh, when this particular antipodal Vivaldi integrated with this surface and exposed. However, if you see the size of this surface, it's just 42 mm, very small in size. and uh, integrating this surface with antipodal Vivaldi that simply splits the beam into more than one. Here, four beam formation. Like, see the kind of the final fabricated hardware. So this is the surface, the reflecting surface. This is the antipodal Vivaldi exposing and getting four different beams in four different directions. That too with a gain of nearly around 12 13 dB. So with 40 size of the reflector getting 13 dB or 15 dB kind of gain, that too split it in four different parts, itself is a kind of good engineering and a kind of a good product. So this is one of the major achievements which we achieved, the beam splitting also from the surface. Earlier, I had shown you getting highly directed beams from transmission type of surfaces. Next, I had shown you getting highly directed beams from reflecting surfaces. Then I tried demonstrating how to split the beams from one beam to two, and as per requirement, again one to four also. Now, in the same, we will try to have multi-beam with switching kind of configuration. So, the surface design, three different switches, and next to this we have 1 to 3 power divider, and depending on that, three different beams switchable in nature. So this is the fabricated surface feet, and again over here at these three feeds with the connectors, we have 1 to 3 power divider which can get connected over here, and with one feet you can get three switchable highly directed beams for the wideband operation. Now, followed by that, we also explored something for high power requirements. When we say high power requirements, that means high power requirements have some special needs. Like our normal dielectric surfaces, they are not sufficient enough for handling high powers. So, the need of having fully metallic surfaces is one of the major tasks. So here we tried achieving wideband performance by using fully metallic phase graded surfaces. So on the top, which you can see here, the 3 4 layer kind of structure, this is completely of metal. Metal means copper, and that copper structure, which is phase graded, and these phase graded structures, when integrated with this shortened conical horn antenna, then this gives very nice performance. So the unit cell here, as I said, that this is a kind of multi-layer structure. So one of the unit cell and then its integrated version, making it wideband. So this is the wideband performance over here. And then after having the complete surface on the circular disc, and this is the respective phase distribution profile, and the respective very nice radiation performance for the wideband, achieving very nice wideband gain enhancement also. So these are the different qualities of different manufacturing techniques and integrating the surfaces with different feeds. In the same way, we have also used fully metallic surfaces for polarization reconfiguration kind of phenomena, where these surfaces are being used for converting or changing the polarization states, linear to circular, linear to LHCP, RHCP, retaining linear polarization itself, or mixed of all these 3 4 different kind of configurations. So changing polarization and configuration is one, and achieving highly directed beams are the next. So, one of the possible problem statement and approach can be integrating both of them, like making the beams highly directed and also having polarization reconfiguration. So, as of now, in this particular work, simple polarization reconfiguration is being shown. So, uh, as I said, we always start unit cell designs from surface, from circuit level approach. So, from circuit to its equivalent performance to the design, we follow exactly the same. And this is finally the fabricated prototype. So the fabricated one integrated over the surface, completely fully metallic copper surface. And we have a kind of control board, which we have designed by using this Arduino prototype and all, which have the capability of rotating the surface on the aperture itself. And by rotating the surface on the aperture, different polarization reconfiguration, polarization states, LHCP, RHCP linear can get formed with high gain characteristics. So in the same sequence, one of that is additive manufacturing technique. Again, multifunctional. Multifunctional means again LHCP, RHCP, retaining LP. But here we have used additive manufacturing technique, like that 3D printing approach itself, where the major task was to achieve ultra wideband performance. So this particular unit cell, the surface design, and again the surfaces are sufficient enough for achieving linear to LHCP, linear to RHCP, so on and so forth, and see the very nice wideband performance from 24 to 36, so on and so forth, uh, and integrating the surface with the feeds. So this is the final fabricated one, and these are the different steps of integration. And this is the setup being tested in the lab, and the respective antenna characteristics. So this particular set works very nicely from 24 to 36 gigahertz band. 12 gigahertz band, giving polarization reconfiguration, giving high gain throughout the band. So very nice performance. In the same sequence, one of the another interesting work is on broadband reflective metasurface, where these surfaces are used for achieving multimode OAM. When I started my discussion that time, also I highlighted OAM is one of the technique which have major significance in 6G technologies. So in our lab, we have also experimented that. There are several techniques of achieving OM beams. Out of that, one is through surfaces. So as our lab have expertise in surfaces means metasurfaces and respective ones. So we used our expertise and designed antennas with different OM modes by using surfaces only. So here we have different OM modes and the surfaces respective one, starting concepts with this as the fundamental unit cell, and it's a different orientations as per the required phases on the surface. Whenever this particular surface will be exposed by your feet in that appropriate frequency band, where this frequency band of the use is from 15 to 45. So when this surface will be exposed by any of the feet in this particular band, this kind of orbital angular momentum based beams can get generated very nicely. Uh, these are some of the sub-terahertz works, again, in terms of designing reconfigurable intelligent surfaces. So different varieties of the unit cells and their different states. So here we have 8 different states. 8 different states means 3-bit configuration and all. And then after integrating, making the surface. So when you will integrate all those as unit cell, after integrating, this will be the complete surface. Since this is the design in sub-terahertz means I am talking this kind of dimensions in microns. So as of now, this dimension is 380 micron, like and some of the line thickness like zero point 0.5 microns kind of stuff, like 30 micron this particular gap, 20 micron this particular gap, 280 microns of this length, so on and so forth. So for 270 gigahertz applications, we have designed this particular surface. And after designing, this is the full surface. The designing itself takes so much of time, and then after integrating, then after simulating, getting the appropriate radiation performances and all, this needs so much of time and effort. And this is a zoomed view of the same surface over here. And then after when you integrate these surfaces, there are different phase requirements which you have to fulfill. And these are some of the plots of those same phase requirements, and hence the same is displayed over here as per the pre-phasing and post-phasing approaches. And see how nicely these surfaces can be used for getting beams from 0 degree to 60 degree, and very nice continuous kind of stuff and continuous kind of beam scanning kind of performances also, which we have achieved by using these types of surfaces. And when this kind of surfaces are used in far fields, in far field means for enhancing the communication characteristic. So on this current graph which you see, one of that is the blue, another one is the red. The red one is slightly larger size of the same reconfigurable intelligent surface size, and the blue one is slightly smaller one. So the larger surface gives significantly higher gain. That means overall around 18 dB of higher gain. That means as and when larger gains are needed, depending on that, the larger surfaces needs to be designed. So these surfaces have uh, very well established nice quality of maintaining, not just maintaining, enhancing the signal characteristic in the channel also. So this proves like how S21, how transmission characteristic can get enhanced in the channel itself without using any extra repeater. Repeater means active repeater. No any active repeater is needed just to enhance the signal characteristic. As far as the reconfigurable intelligent surfaces are concerned, they are well sufficient enough to achieve around 18 dB of gain, which we have experimented at our lab. And when you fabricate these micron levels of unit cells, micron level of surfaces, they simply looks very nicely something like this. And these are some of the unit cells printed, the printed ones. And these are different cable connections to excite it, to make it reconfigurable. And this is something which we need for the complete transition from 5G to 6G and so on and so forth. So I have given a wide view of the technology till now, uh, where these frequency selective surfaces, these unit cells, how nicely they can play various different roles as far as intelligent reflecting surfaces and integration with antennas are concerned. So I tried presenting some near field and some far field approaches, and these techniques are very nicely well experimented at our lab with our facilities, and it works very nicely. By this, maybe the technical side of the talk, I would like to stop. And before that, just if any one of you feels interested, then currently we have large recruitments also going on with our group, with postdocs, research scholars, and all these positions are project based. So if any one of you finds interested, directly they can approach through email or to the web pages and all. And again, I will request all of you, if you are IEEE member, it's very well and nice. If you are IEEE member, try to get involved with Antenna Propagation Society, Microwave Theory Technique Society, get its membership. And I hope your institute at Jaipur, you have very nice chapter and very nice volunteership of Antenna Propagation Society and Microwave Theory Technique Society. Those of the attendees who are not member of this kind of society, I will just suggest give a chance once to the society, and you will see how nicely the benefits you can get from this kind of societies. So if you invest one penny, for sure you will get more than 10 times of that as benefit. Try and explore as much you can with our Antenna Propagation Society. And as far as our society's membership is concerned, it simply costs one USD if you have IEEE membership. So just a nice request and suggestion for particularly for youngs, if you wish, for sure, please join us, and please uh, try to get involved with society operations, society activities. One of the major benefit of being part of this kind of societies are this society supports you in attending their flagship conferences in so many ways, financially, economically. They also do the arrangements of your stay, how, particularly for young researchers, students. So try to get involved with the society and the conferences as much you can. Uh, I would like to stop here itself, and then more of I would like to take the queries related to this. If any one of you have, it will be very nice to discuss all these stuffs.
Thank you, sir. So we have a few queries.
Yes,
May I ask, sir?
yes, please go ahead.
Sir, first question is how to decide the geometry of the unit cell to achieve desired radiation pattern.
So, as I said, unit cell design itself is not like designing any kind of shape itself is not appropriate technique. So, going for the design of a unit cell, always start from circuit level. Circuit level, why I say circuit level? The fact is, every surface is a kind of filter, maybe band pass, band stop, as per the requirements. Sometimes all pass also. So just the idea behind designing of the unit cell is how you design a surface, how you design a filter. So, for example, for a band pass filter, you need appropriate combination of inductors, capacitors properly arranged in some fashion, connected in series and something like whatever. So, in that way, when you connect those inductors and capacitors, like first order, second order, or even more than that, so depending on the required performances, then after those inductances and capacitors are converted into strip line structures. And there are very well established technique how to calculate and how to find out the dimensions of strip line structures from equivalent inductors and capacitances. So we follow exactly the same approach, and this is one of the standard one to go through. So audience can also, the one who have asked this question or even others also may follow exactly the same approach while designing this kind of unit cells, and that will give complete insight regarding the unit cell level of designs. Yes.
Thank you, sir. Sir, with respect to work number one, how the
How the
variance and number of unit cell is decided?
how the
Number of unit cell is decided, like 4-bit, 2-bit are used in a RIS. So how it is decided that how many we have to use?
it's not like how many we have to use. It's completely depending on the size of the surface and the capacity of the unit cell. So if your unit cell is sufficient enough to go for 3 bit, 4 bit, or even more than that, it's well and fine and well appreciated as well. Because as much precise quantization you do, that much good performance will be. However, as I cited, that every unit cell have its own limitations. Limitations means, for example, if you have designed one fundamental unit cell, by using that fundamental unit cell, you cannot go for more than 2 states or so. That is the limitation of that particular unit cell. When I say the limitation of that particular unit cell, I am not saying in terms of geometrical parameters. I am saying in terms of the performance. For example, if your unit cell is reflective and you are designing a reflective surface, then your unit cell and its variant should follow that particular reflectance magnitude and phase also. So, depending on the unit cell and then the surface size, the number of different states of the unit cell can be decided and considered.
Okay, okay, sir. Sir, next question is there any your paper in which it's available that how to design a geometry from circuit level? If no, can you please recommend any reference?
Yes, we have several papers where we have directly discussed the circuit equivalent analysis from circuit level to unit cell level of designs. and you can find it on IEEE Explorer. So it's well nicely available. You can have a look. And also, this kind of techniques are very well standard defined in my book also, which we have. I have authored that particular book, and that is on metamaterial itself. And this nice techniques and steps very nicely discussed in that.
Good morning, sir.
Yes, please.
Sir, I am working on FSS based absorber structure. So, for absorber, when we are using it as a application of shielding, then how we can calculate its shielding effectiveness?
So when you say shielding effectiveness, that means you are talking in terms of absorptivity.
Yes, sir.
So see, as far as the calculation is concerned, for calculation also there is well-established formulations. And these formulations are again from the state of art, like that mushroom kind of absorbers when was invented by uh, Chu probably. So in his paper, that time itself, he proposed those procedures and steps, and even those procedures are very well defined and very well suitable till now also. Like that, with respect to your unit cell performance, like reflection and transmission characteristics, magnitudes and phase taking all together, how these reflection and transmission coefficients like S parameters, how you can correlate and get absorptivity depending on your sizes and uh, your surface type. And from that itself, you can also calculate the effectiveness. So it's well available on literature also. So you can cite those things for that purposes.
But sir, in the shielding effectiveness formula, there is only S21 parameter which is there. S11 it is cancelled out. Only
Yes,
S21 is there. But
yes.
when we are talking about a absorber point of view, the ground plane is completely filled with metallic plate. So by default S21 is zero. Means in absorber we know S21 nearly about zero.
Mhm.
So when in absorber, if S21 is zero, how can we put those S21 value for the calculation of this shielding effectiveness?
Okay. So see, absorbers, when you say, not necessarily should have metal in the back. However, out of several designing techniques, there is one where you can have unit cell on the tops and the bottom surface completely metallized. So in that cases, your transmission is zero. So in
Okay.
that cases, when your transmission is zero, so simply in your formulations, use that data only. Like by default, you simply consider that transmittance is zero, and the complete absorptivity will simply depend on your reflection. That's it. Reflection means magnitude and phase both, complex value. When you have the same absorber without metal background, at that point of time, you have to take both of the parameters.
Means sir, if we have a ground plate at the bottom surface, then whatever value will come as S21, we can directly put it.
Yes, you can S21 you will have zero because you have on the back metal. So simply put S21 zero and take only S11 data. And depending on that, you will calculate absorptivity. 1 minus something mod of S11 square, so and so forth. So that particular one, you can simply take the data and have MATLAB code, incorporate those data, you will get those absorptivity.
Okay, sir.
Participants, you are requested to ask, and if you have any queries. Sir, I think now there are no more queries.
Yeah.
On behalf of EICT Academy, MNIT Jaipur, and Electronics and Communication Department, sir, thank you very much, sir. The session was very much fruitful.
Thank you, Swati, for
Thank you very
inviting.
much, sir.
And thanks, attendees, for joining. Even if you find any question, any comments, your question and comments both are welcome over email. Uh, uh, Thank you.
Thank you, sir.
Thank you. Bye.
Dear participants, next session will be start from 5:30 p.m. in the evening. You are requested to kindly join by time.